All right, trigonometry review for calculus, again, placement test. This assumes you've been in pre-calculus. This is video 3. If you haven't learned this, this is going to go too fast and be too hard. That said, we should understand the bow tie, as we call it here at Juda schools, of triangles in the 4 quadrants. And there's some relationships we should know. And I have them over here. You know that when we look at the triangle in the 1st quadrant, and in the 4th quadrant, we can see that the cosine of those 2 triangles is going to be identical. And if, in that case, when I say that, it means that the adjacent leg over the hypotenuse, they're both positive. Because the hypotenuse is always positive. It's a distance out to that point out there at some angle. But then the hypotenuse, they're both positive. Likewise, you can see the sine relationship again. This is a positive, and this is a positive, but on the underside, this is negative, this is positive. So that makes that relationship true. And finally, we should be able to convert pi to radians. But if we look here at this situation, we can see that this kind of makes, as you go around, this can make a circle. And that's not a great circle, but at some radius distance. And the easiest distance to have is a distance of 1, which we call the unit circle. And again, we can do all our triangles on this unit circle. So I put a point xy at the unit circle, and it's out some distance of 1. And what we can see is, not only does this give us the general form of a circle centered at the origin, where Pythagorean theorem leads x squared plus y squared equals 1 squared, or r squared, it more importantly, in this case, leads to our understanding by using simple trigonometry that if we have our trig based on the reference angle of theta, that the y is always going to be sine theta, because sine theta in this case would be y over 1, and cosine theta would be x over 1, or x equals cosine theta, y equals sine theta. So we have always said x is cosine, y is sine. When you use the reference angle, we are not using, we don't prefer to use this. It will work in your calculator, but for sure we do not want to ever use this angle. That said, this is the unit circle, and we can do lots of things with the unit circle. And what this allows us to do is to consider situations using the points here. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. We can literally take, and if you take your calculator, you can do this, we can take the cosine of 0 degrees. And in this case, it's this blue line out distance 1, that will be 1. The sine of 0 degrees, the y value at 0 is 0. And if we work our way around, we can do all the points, as you recall. So cosine of 90 degrees. If I look at this point up here, cosine is x. Well, that's obviously 0. When I say 90 degrees, or pi over 2, we are going 90 degrees, or pi over 2 radians here. So if I say sine, maybe I should do some in radians. Pi over 2, that's 1. And so on and so forth. So if I do that, I can go all the way around. We can see, then just looking at 180, that cosine of 180 is negative 1, and cosine of 180 is 0. And then if we look at here, 270, right, around 270, we can see that cosine of 270 is 0, and sine of 270 is negative 1. And we should be familiar with all of these. But more importantly, the last thing is we can do all our unit circles thinking about our standard triangles, which I've drawn here. And I'm trying to get the spot where I can make it a little bigger. There. Now the problem with our 3 standard triangles here, and I show a 30, then a 45, then a 60, as we go around, is that those would be on, here's 30 degrees, there's 45 degrees, there's 60. All right? But the problem here is the hypotenuses on none of these triangles are 1. So we can remember that we can do ratios. So the 30-degree triangle has a point of 1/2 comma square root of 3 over 2. You can divide by square root of 2, square root of 2, square root of 2. Now we want to rationalize. So this point is square root of 2 over 2, comma square root of 2 over 2. And finally, the last one we can divide by 2, and again, it's the same as the other one, except we flip-flop. I have this point backwards. My bad. I got to do xy. Square root of 3 over 2, 1/2, and this one is 1/2 square root of 3 over 2. Once you have those three, they repeat going around. These are reference angles. So 30° over here, the only difference with this point in the first quadrant versus the second, if I put it over here, x is negative square root of 3 over 2, and y is still positive 1/2. We can go all the way around doing that. And again, this should ring some bells. If it doesn't, you need to find a unit circle thing and watch. So the problem here is that literally, if you're not bound, there can be an infinite number of answers. So keeping this in mind, if I say sine of x equals 1/2, first thing you got to say, hey, what quadrants is it positive? Well, it's y, because it's sine, so it's right there. It's a 30° angle, right? But the problem is it's not only 30, it can be also in the second quadrant where sine 5. So it's 30 degrees. 180 minus 30 is 150. But the problem here, then remember, is it can go all the way up, around again. So 360 plus 30 is 390, and so on and so forth. Infinite number of answers. Now, in the placement test, they usually don't go after that. They usually bound you to 0 to 360. But again, we should be very quick to find these values. Again, identifying signs of quadrants. But that leads us to this discussion. How do we bound it? So what if we have arcsine, arccos, arctan? That is a bounding system versus doing this. All right? On the last example, we had sine of theta equals 1/2. Well, that meant theta was sine negative 1/2. And that meant there was an infinite number of answers. We could go around the unit circle over and over and over for the first and second quadrant and have an infinite number of answers. All arcsine and arccosine does is give a notation saying, hey, we don't want infinite answers. We want to bound this. We want to bound this to the quadrant as close to quadrant 1 as possible. So we know that arcsine, cosine, and tangent are all positive in quadrant 1. So when we can, when the arcs, we want to be in quadrant 1 for all three. The closest quadrant that's negative for arcsine and arctangent is quadrant 4. So for positive, all three, arcsine, cosine, and tangent, are all positive in quadrant 1. That's our positive cases. And if I do the negative cases, maybe in blue, two of them are here, arcsine and arctangent. And that just leaves one, arccosine, to be negative over here. And that's just asking for one answer. And your calculator will give it to you this way, in negative cases. All right, so a lot of times they can do it two ways. They can say, oh, let's do arcsine, a positive 1/2. Oh, that's easy. Positive is in the first quadrant, 1 over 2. And again, you should immediately recognize that as a 30° triangle, or pi over 6 for radians. All right, likewise, by changing to negative, the triangle simply becomes in quadrant 4 because it's negative over that. All right? But a lot of times they do goofy stuff. They might say, hey, what's the tangent of our cosine negative 3/5? This is something on placement tests a lot of times. And you got to ignore the tangent. You got to start saying, hey, I got to find the angle inside first. We got to deal with this first. Well, our cosine, and when it's negative, it's not quadrant 1. The closest quadrant is 2. So then 3/5. Well, 3 and 5, right? Adjacent over hypotenuse. All right. You see why I picked this, because Pythagorean theorem, again, it's a right triangle because it's trig, 3, 4, 5. Well, now that's angle, I'll call it A. Well, this is angle A, so the tangent of A. Well, I look at that. 4 is positive, 3 is negative, because we're in the second quadrant. Again, I should have labeled my axis. And so the answer to this problem is negative 4/3. And again, you can find practice problems like that to work on. Doing sine, cosine, and tangent takes practice. And we just did a very quick review of radians and that, our placement on the unit circle and solving for multiples. And again, arcsine, arccosine, and arctangent. All right, we're going to have one more video after this, and we'll go from there. Keep practicing.